more. Okay, this is just a quick question. I'm trying to schedule a final exam review session, so I wanted to see what your preference was. I think that you should choose Friday because your final is on Monday, just so you know. So you might not want to wait until Sunday, but I just wanted to know your thoughts on it. Our final is on the first day of finals week. Also, I'm going to be running the final review session. Probably have some TAs there too, but we're all going to be there. So do really great things. It's going to be really great. I'm going to love it. Everyone in? Okay, let's stop it. Probably swayed your decision a little bit, but that's the way I like to do it. I know. Yeah, so Friday was the most popular. The 2 Fridays were the most popular, but at least I know when you are available. Okay, hopefully this records this time. Didn't record last time. I'm not wearing the mic again. All right. Still recording. Good. Okay. So we just finished the topic 9, which was data analysis and statistics. So remember what we were doing in that topic from a bigger perspective is we were thinking about how to summarize data into singled numbers. So how can we tell a story with data with some sort of metrics that are smaller in size? So we're going to kind of continue that storytelling with data with curve fitting. And the next 2 topics are both continuing that story. And so I'd like to talk about them because I feel like they can be often confused by each other. So let's say you have some data that I have marked with the black dots. Curve fitting is to find trends in your data, analytic trends in your data, and it's determined to be a best fit curve. So that's what we're going to be doing in topic 10. Topic 11, the next one that we're doing after this, often gets confused with curve fitting, or they get switched commonly, which is interpolation. So the way you want to think about interpolation is you have a set of data, and you need to find data that is between the data points that you've already collected. So let's say we wanted to know what point existed between these 2 points here. We would need to interpolate between the 2 points. So I think this little visual kind of just reminds you of the difference when you just see it. So today we're going to be focusing on fitting curves to data so that we can get a general trend in the data to see what the relationship between it is, where interpolation is to find data points that you didn't originally collect or get. So we're going to do this in this topic using least squares regression. And I'm going to show you how you get to the equation that you're going to program. Some people call that a derivation. Some people don't like them. But this one is great. So just stay tuned. So assume that you have collected some data or you have received some data. and it's two sets of data, so x's and y's, that have some sort of a relationship. And you want to find a best fit line. And since we're going to do linear, we are going to look for a linear fit to the data. And you can thank me because it's a lot easier to program that than it is to do any higher order. This is the kind of thing that you might do in 303. You could do higher order interpolation or regression. And so these are what you expect them to be, the y-intercept and the slope. Okay, so to do that, we're going to define something called a residual, which is a common term in modeling and in statistics and stuff, if you've never heard of it. And residuals are like extra stuff. That's like the most scientific term, or scientific explanation. And it is the difference between the true value of your data and the approximate. That is predicted by your linear approximation. So it really helps to draw out what that says. So that's what I'm going to do for you. So let's say that you have some data on an XY plot. So I'm going to draw out just a few points. And then you have a fit, a best fit line. You're going to choose that best fit line based off of the smallest difference between what that line is approximating and the actual y value. So let's say that you are looking at this point here. Let's call this point x of I. Its actual value is right here, y of I. And the value that is approximated by the linear fit is right here. And if it's a linear fit, then that value will be mxi plus b. So we define the residual r of I equal to the difference between the actual true value and the approximated value from the fit. And so the R value is right here, is that vertical distance between the data point and the line. So in order for that to be considered a best fit line, you would want those R values to be as small as possible, right? So you want to minimize those R values. So anytime you've ever used a fit line in Excel, if you've done that in labs before, you can do a quadratic fit or a linear fit. All it's doing is it's finding the path that makes those R values as small as possible over the entire data set. So that's what I'm going to show you. How you get that. So how can you use that information, the data and the linear approximation, to find that line? So you basically want to set m and b, the slope and the y-intercept, in order to minimize the sum of the residuals. So you want to look at all of the residuals and find the minimum of all of them. So we're going to create an equation that I'm going to call S, and that equation is going to be the residuals. And because we don't care whether the line is above or below, just like what we did with the standard deviation last time, we're going to square the residual to get rid of the sign. And we are going to sum the residuals over the full length of the data. And then we're going to minimize that equation. So let's plug in what the residual is in terms of our data. So the residual is yi minus the approximate value mx plus b, and that whole thing is squared. So the thing that gets most confusing about this is keeping track of what is known and what is not known, because through calculus and math, you always think of x and y's as your unknowns. But remember, x and y is what we know in this case because it's our data. So that's given. What we don't know is the m and the b. So if you want to minimize something, what do you do in calculus? You take a derivative and you set it to 0. So we're just going to differentiate our equation with respect to the variables that we're trying to minimize, or that we're trying to set to minimize. So the two variables we have are m and b, so we're going to differentiate with respect to m and b. So maybe, okay, this is fine. So this is our equation. These are our unknowns, so we're going to differentiate this equation. So this is the chain rule, so we're going to move the 2 out of the sum. And then we're going to take 1 out of the power. So that's just going to be a 1. And then we have to take the derivative of what's on the inside. Does anyone know what that is? It's 1, and it's also negative 1. I mean, it is negative. It's just negative 1. So it's negative. So we're going to multiply out the derivative of what's on the inside. So there's a negative b, so the derivative of negative b is negative 1. So that's our derivative. Then we're going to also differentiate with respect to m. So again, we're going to do the chain rule, power rule. You know, it's all really the same, right? Just math, rules. So good. I love math. I'm just trying to talk while I'm writing this. You guys are all writing too. I don't need to talk. So what's the derivative of the inside with respect to m? Negative xi. So I'm going to put the negative out here and the xi out here. So we did that, and now we're going to set them equal to 0. So now I'm just going to rearrange this. I'm going to collect like terms. My first like term is going to be no m's, no b's. Second one is going to be m's. Third one is going to be b's. Okay? Okay, guys? Got it? Do you like this? This is kind of fun, right? The honest thing is that you don't need any of this to do your project. But you need it for depth. You need to know what you're doing. You know what I mean? It's just derivatives. Now no one's even listening to me. Okay, so these terms are no m's, no b's, these first terms. Oh, maybe that's the problem. Yeah, that's definitely the problem. Okay, the second term is all the m terms. So we have an mx squared, and then the last term is the b term. So all I'm doing is rewriting the two equations set equal to 0, and I'm collecting like terms so that I can tell you more about it. Okay, so these are our two equations. Maybe I'll even label them. This is 1, this is 2, and then I'm just rearranging them a little bit to be more convenient. Okay, so now I didn't do anything except for distribute the sums through, but I didn't do anything fancy with the sums. So now I'm going to just do something kind of, it's a little bit fancy now. So what I'm going to do is I'm going to set up the sums in a little bit nicer way so you can kind of see what they are. So here I just distributed the sum out. By the way, divided by the -2. I got rid of it 0 on both sides, or 0 on one side. And then I just distributed it through. So now what I'm going to do is kind of simplify some of the sums to make them a little bit easier. For example, now I want to have bm equals the rest. So this b term is what I'm going to start with. So can anyone tell me what the sum of I equals 1 to n times of b is? What did you say? It's b. How many b's? N b's. NB. It's NB. So you're summing b n times. So there's n b's. So it's the same thing. These two things are the same thing. So you can also do the same thing here. We'll just pull out the m of this term here. And then there's nothing to do with the term without the m or the b. All right, we're going to do the same thing to the other equation, equation 2. We are going to pull the b out. So now we have b times the sum of xi, I equals 1 to n. Pull the m out of this term, so now we have m times the sum of xi squared. And then we're left with the sum of the product of x and I. So now we're left with this, and this is two equations and two unknowns. So the only thing unknown in these two equations is m and b. You have two equations, so you can completely solve for m and b, right? If you have two equations and two unknowns. So I'm not going to go through all of the algebra for that. I'm just going to write down the answer, which is what you are going to use in your programming assignment. So you guys know how to solve two linear equations with two unknowns, I am sure. You can use all sorts of methods, and this is what you get for b. Can anyone tell me what 1 over n times the sum of yi's from 1 to n is? What'd you say? That was right. I can't hear anything. It's not 0. It's the mean of y. Yes, it's the mean of y. Y bar minus m times x bar. So that's actually pretty nice. Like, you already know how to do that. So that's b in terms of m. So then m can also be solved for, and this is what you get for that. Not as nice, but it works, and it's all in terms of your data. So you can go through and do, I'm sure you all will, you'll make sure this is right, and all the algebra. So this is an entirely in terms of x, the arrays x and y. And as you can see, it's a bunch of sums again, which you guys know how to do. But you need one of them. So you either need M or B so that you can plug it into the other one. I don't know who said that, but I'm looking at Joel. Is that who said it? Okay, great. Yeah, you need one of them in terms of all knowns, and then the other one can be in terms of the other one. The other one. So I'm going to show you a little bit on MATLAB with this, and then I'm going to show you some nonlinear relationships. So I feel like people are still writing that down, but you need this on your toolbox card. All these equations you need to have on your toolbox card for the exam, so make sure you have them. What else can I talk about while you finish writing? Sure. So what I'm going to show you is using the intrinsic functions. I'm going to apply these equations, and then you're basically going to be doing the same thing in your lab, but with your own function that you write. But you can see it's pretty easy to write this function if you have a sum function written already. Is there a question? All right. So I'll come back to this. I'm going to write more. So what I wanted to show you really quick is just a quick example with this. So I have two sets of data. I have the voltage across a capacitor and time. I chose this because it has an exponential relationship, and I wanted to show you something with a nonlinear relationship. So I'm just going to show you what the data looks like before, before I actually do any fitting. So this is what the data looks like. Let me make that a lot bigger. Okay, so that's what the data looks like. So you can see it's not really linear. So a linear fit won't be great, but we can at least see what a linear fit gets you. So the way that you can do that with the intrinsic function, it's called polyfit. There's a bunch of polyfunctions actually that do a bunch of different things. You're going to see them in your pre-lab. But the polyfit function works by you plug in the two arrays that you would like to fit data to. So I've plugged in time and voltage. And then you plug in the order of the fit. So since we're just doing linear, we're just going to do order 1. But you could also do quadratic, cubic, whatever. The output is an array that I'm putting the values into called A. And what A is the M and the B of the equation for the fit. So we got out these two. So I redefined each of the elements of the A array to M and B. So I put the first one in the slope and the second one in the y-intercept. And then I just took my X array time and I multiplied it by the slope and added the y-intercept. So I could get my fit line. And then I'm just going to plot my fit line over the top of the data. So this is what you'll do as well. And this is what it looks like, you know, when it doesn't have it there. And that's the fit line. I don't know, why did I pick these colors? Green. Let's do black. So that's how you use the intrinsic function. And what you're basically going to do is write the same function, but only for linear. So you won't have variable order. And your final plot will be similar. You'll have data and the fit for that data. So now what I want to talk a little bit about is how to use a linear fit for nonlinear relationships. And then I'll show you how you can do that in MATLAB as well. So I'm going to show it for an exponential fit. So what you can do is if you have a nonlinear relationship that's either exponential or power, you can just linearize the equation and still use a linear fit, which is a way you can fit to data that's that in a simpler way without using a more sophisticated fit like a spline fit, which is pretty messy. So if you just linearize an exponential function, if you remember this from this, you actually did this sometimes to like do some derivatives. I think this method was used in calculus. But to linearize, you're just going to take the natural log of both sides to get rid of the exponential. That's allowed. Math allows you to do the same thing to both sides of the equation. And then you just do a little bit of algebra to simplify it a little bit. So how do you split up a log? If you have two things multiplied inside of a log, how do you split them up? You add them. I don't know if anyone said that, but I think you did, definitely. You add them, and then now we have the exponential by itself, so we can pull that out, and now we're just left with natural log of y equals natural log of a plus bx. And you're probably thinking, okay, so what does that mean? And this is now linear because the relationship with x is linear. So what you can do when you perform, and it's linear because of this. If you have the log of y on the y-axis and the regular x on the x-axis, your relationship, your slope is b, and your y-intercept is the natural log of a. So that's linear now because we took the log of both sides. So you can use linear regression by putting into the poly function, or your linear regression function that you write, instead of just putting in x, you can put in the data x, comma, natural log of y. So you're linearizing the data before you're putting it in the regression. And when it comes out, you get those a coefficients or whatever that represent the slope and the y-intercept. Then you just need to kind of like go back and take an exponential again later. So I'll show you how you do that. So a, if it comes out with a, I want to make sure you have this written down so that you can remember. The first element of a is the slope, and the second element of a is the y-intercept. So because we put x and y into our polyfit function, that means that our fit corresponds to that the m times the x plus the b is going to equal the natural log of y. So if you want to plot it after you get it out, then you just need to take the e of both sides. You guys, this doesn't make very much sense right now, but it will. You just take the exponential of both sides, and then it will be an exponential fit. I'm really doing bad on this scooting up thing. Scoot down? What did someone just say? Scoot down? So I'm going to show you that here in MATLAB as well. But the idea is that you linearize the data before you put it in the linear regression model, and then when it comes out, you just have to apply the opposite of what you applied. So because we took the log of y, when it comes out, we have to take the exponential back. And I'm going to go back over to show you it in this example. So what I did here is I called the polyfit function another time. I put in the x, and then I also put in the log of the y, and I did the linear first order. I got out the coefficients for the m and the b, and I defined them the same way. But then when I defined my fit, my exponential fit, I didn't just do mx plus b, but I took the exponential of it because I have to go backwards from when I took the log of the initial data. And then I'm going to plot it with a red line. And let me just increase the line width real quick so you can see a little bit better. Okay, so this is what it looks like. Honestly, I made this data up, so that's why it fits perfectly. But it is a very good fit, the exponential fit. So you're going to do this with your lab too. You're going to try a linear fit, but then you're also going to try to linearize assuming the data is exponential, and then do it this way too, so you'll have two different fits. The last thing that you're going to do is relate the stuff from last topic, correlation, to fit. So I wanted to talk just a little bit about that. So that's why if you probably couldn't see it because it's really small. So remember, you have your data, and then those equations that we derived give you this best fit line. And then the best fit line is minimizing all of these r distances, these residual distances here. And this is directly tied to the correlation coefficient. So as the correlation coefficient, shouldn't really say this, but as it goes down, the sum of the residuals should also go down. So that's opposite, right? Is anyone following me? I think it should be opposite. So as it's less correlated, it's going to be more spread out and less in a line. And so the distances should be greater. I think I just wrote this wrong. The sum of the residuals. So you want the sum of the residuals to be as small as possible, but the sum of the residuals will be greater if there's less correlation. And when I say goes down, I mean closer to 0. So less correlated. So as there's less correlation, as the data is more spread out, you should have higher sum of your residuals. So what you're going to do in your lab is for all the data that you're comparing, you're also going to plug that data into the correlation coefficient function that you already wrote, and you're going to include that correlation in your legend to show, and it should make sense. So data that has a worse best fit line should be less correlated as well. That was so great, right? I will see you guys next time in lab. What's up?
I just want to ask you, so
Yeah.
when I was studying calculus, we were having sums, and I tried to use this in MATLAB, but I got an error, maybe formatting. You know how to, is it the true for,
That means it's a symbolic sum.
it said sum of the series in your website.
Yeah, so SimSum is, we haven't used it, we used it in the last topic, but it's a symbolic function. So it doesn't use data, it uses like symbolic notation.
Yeah, like in the calculus, right? Like,
Yes, but you have to set up all of these as symbolic variables.
that's what I tried. Can you show me?
Yeah, I could. You want to come to my office after this, and I could show you. It'll take. It's a little bit longer than just a quick answer, but I'm happy to show you. If you want to come to my office right now? Yeah. Hey.
Hey, so I just had a quick question that you said that our final was on that first Monday. Yes. Are you going off of the time that we have this class?
Yes.
Okay, because I've been finding before and I thought it was on Thursday because I was counting the lab as that. So I was just double checking that
right.
was on.
No, it's
I
the
couldn't,
lecture
because I couldn't
class.
find a time